All right, so today we're looking at Taylor polynomials. Now this covers both day 1 and day 2 of Taylor polynomials. So if you just need day 2, you might need to fast forward a little bit. But Taylor polynomials is the idea of having a polynomial approximate the a function that is not normally modeled by a polynomial. So we're going to start by looking at an example. You can go ahead and graph this, but I'll pull it up right now so you can see it. Okay, so here's the calculator and here's the graph. We'll notice that on this center segment here from about -2 to 2, these look like pretty close to matching models of each other, but as you get further away from that center, you start being less and less accurate of models. That's because this function of x minus x cubed over 6 plus x to the fifth over 120 is what we call a Taylor polynomial. It is an approximation for sine. So let's look at how we actually create that Taylor polynomial. This is all the formula for a Taylor polynomial and Maclaurin polynomial. You can pause the video and write it all down, but I'm just going to talk about what it's saying. So this is saying if we have a function f that has n derivatives, then this polynomial is going to be an approximation for f of x. And the way we find it is we take our center, and usually it tells us what our center is, but it's c, and we'll plug it into f, and then we'll add the next term, which is the first derivative of f of c, x minus c to the first power over 1 factorial. And then this pattern continues. The second derivative of f at c, x minus c to the second power over 2 factorial. Third derivative of f at c, x minus c to the third power over 3 factorial, and so on and so forth. Now, a special case of this is when you end up with c equals 0. Notice it doesn't change anything about the formula. It just has 0 plugged into c. We call this a Maclaurin polynomial. Now, the one thing to make sure you understand is the difference between the degree and the number of terms. So, for example, if we look at this, this is the third degree polynomial, but it has 1, 2, 3, 4 terms. Similar things happens on this first problem. This would be the fifth degree polynomial, but it only has 3 terms. So make sure you're keeping track of what the question is asking for and whether it's talking about the degree or the number of terms. So let's look at our first setup. So this one's given us a lot of information about f. One of the big things we can identify is since it told us that 2 was plugged into all these, that's going to mean our center is 2, and we see that said here. Also, it gave us 1, 2, 3 derivatives, which means we're probably looking for a polynomial degree 3, which it told us there. So let's go ahead and just plug this into our formula. Now, since the polynomial is an approximation for f, we're just going to put f is approximately this third degree polynomial, and we use P3 as a naming structure. I've also seen T as a naming structure, but we use P. So we have, technically, this is going to be f of 2, the 0th derivative of it, x minus 2 to the 0 power over 0 factorial, plus the first derivative at 2, x minus 2 to the first power over 1 factorial, the second derivative at 2, x minus 2 to the second power over 2 factorial, and then the third derivative at 2, x minus 2 to the third power over 3 factorial. Now, we don't need to write all of this out every time. This is just to emphasize the pattern that we're creating here. And it's going to be the same pattern every single time. You're going to start with the 0 power and 0 factorial and 0 derivative, and you're just going to keep going up by 1. So if we look at this, this is just f of 2. That's going to be 3. X minus 2 to the 0 power is 1. 0 factorial is 1. So 3 plus, then f prime of 2 we're getting from up here. That's going to be -4. And then x minus 2 to the first power over 1 factorial, which is 1, plus the second derivative at 2, which is 7, x minus 2 to the second power over 2 factorial, which is 2. And then we'll have a minus 5, x minus 2 to the third power over 3 factorial, which is 6. And this is our polynomial. Now, you can technically simplify this and combine some like terms, but you don't need to. You're not required. We're just setting up the polynomial. Let's look at another one. All right, so this one is asking for a Maclaurin polynomial. Maclaurin polynomial just means it's a polynomial where the center is 0. So that means it's telling us, hey, C is 0 here. Now, this one's a little different because it didn't tell us all of our derivative information, which means we're going to have to find it. So if we want the nth degree, that means the 5th degree, we want 5 derivatives. So let's take 5 derivatives. It's going to be cosine, if I actually wrote it correctly, oops, cosine of x, negative sine x, negative cosine x, sine x, and then cosine x. So there's our 5 derivatives. And then we want the value of each of these when you plug in our center, which in this case is 0. So we'll start with f of 0. That's going to be 0. F prime of 0 is 1. F double prime of 0 is 0. Third derivative of 0 is negative 1. Fourth derivative of 0 is 0. And the fifth derivative of 0 is 1. And now we're just plugging that into our polynomial expansion, our formula. So we have the 5th degree polynomial this time. We have 0 plus, and then 1 x to the 1 over 1 factorial, which is just going to be x, plus, then 0 x squared over 2, minus x cubed over 6. Technically, it's 3 factorial. Let's write 3 factorial for now. 0 x to the 4th over 4 factorial, and then plus x to the 5th over 5 factorial. A little bit of simplification here. We see this as x minus x cubed over 6 plus x to the 5th over 120. So there's our polynomial, and we've seen this polynomial already today. This is the polynomial we graphed at the very beginning to show that it is an approximation for sine. Now, if we think back to that graph we made earlier, it loses some of that accuracy as an approximation as you get further from the center of the graph, or what also is the center of the polynomial, 0. So if you go back and you look at the graph that we saw earlier, you'll see that the further you got away from 0, the less accurate it became. And we can actually see that by testing some values here. So P5 of 1.4 is our polynomial approximation at 1.4. F of 1.4 is our actual value of 1.4. So let's go ahead real quick and see what each of these equal. Okay, so if you plug these into the calculator, you should get 0.987 and 0.985. You can plug them in on your own if you want. So this is our approximation, and this is our actual. So we can see that it's not exact. It's not going to be exactly correct, even though we're pretty close to 0. 1.4, I would say, is pretty close to 0. So we can find the error in that approximation. Now, if you've done any form of science that does error, this formula should look familiar. This is actual minus approximation, which gives us the error. And so we can plug that in the calculator, and we should get 0.002 for our error. So we see we're only 2 thousandths off. It's a pretty close approximation. Now, on your own time, you can check these two, and you should be able to come to a conclusion about what should happen before you even plug it all in. We see that 2.1 is further away from the center than 1.4 was, so you're probably going to end up with a bigger error. So I'll let you check that out and see. So let's move on to the day 2 material. Day 2 is just looking at some things we can gain from these polynomials, from understanding these polynomials. So let's look at this problem. We have a graph of f, and we're given that the 2nd degree polynomial is this right here, a, b, and c. All right, that's the 2nd degree Taylor polynomial about x equals 0, so centered on 0, or in other words, it's the Maclaurin polynomial. What are the signs of a, b, and c if f has a graph pictured to the right, and explain your reasoning. Now, this process, I think you should be able to do on your own. I want you to pause the video and try it, and then you can resume. Okay, so I'm assuming you've paused it and tried. This information should be able to be gained if we understand the formula of a Taylor polynomial. So we know that A has to be f of 0. So that is the function's value at 0. Let's put it this way. A is f of 0. Now, we don't know what that function's value is, but we can see it here on the graph. It's above the x-axis, so this should be positive, okay, which means A should be positive. So let's write this so that we can explain our reasoning. We should say A is greater than 0 because f of 0 is greater than 0. All right, well, what about B? B is, since it's in front of the x term, should be f prime of x, well, f prime of c, so f prime of 0, over 1 factorial. Now, 1 factorial is always positive, which means the sign of b is just going to be whatever the sign of f prime of 0 is. And some of y'all are saying, well, we don't know what f prime of 0 is, but we do know what f prime of 0 represents. F prime of 0 is the slope. So if we look at the slope at this point, we have a positive slope. So b is greater than 0 because f prime of 0 is greater than 0. Okay? Or in other words, we can say because, since the function is what they give us, because f is increasing. All right, well, c follows the same pattern. C is the second derivative at 0 over 2 factorial. All right, well, once again, 2 factorial is always positive, so that means the sign of c is the sign of, sign of f double prime of 0. Once again, we don't know what that value is, but we can gain some information from the graph. The graph is concave down at this point, which means the second derivative should be negative. So c is less than 0 because f is concave down, but also because f double prime is negative. So we'll say because f is concave down. Okay, so there's some information that can be gained from these polynomials, or that we should be able to gain from the function about these polynomials if we understand how the formula works. Oops, too far. Okay, this is another one we can see. We're writing the third degree Taylor polynomial for f about x equals 3. I'm going to go ahead and jump ahead and get this written, and then we'll talk about b. You can pause the video and try on your own if you want. Okay, so here's our expanded polynomial. Now we'll notice this is centered at 3. So and when we look at part B, it wants us to find f of x squared plus 3. Now in a normal problem, you would assume you just plug that in, but we need to check something first. Does our center realign? Realign. Now, what do I mean by that? Well, originally our center was at 3, but if we're doing f of x squared plus 3, that shifts the function. If you think back to what happened back in your pre-calculus algebra 2, if you added a number inside the parentheses, that shift the function to the left. So that means our center needs to be shifted to the left the same amount. Well, previously we were centered at 3. We're shifting to the left 3, which means our center should be at 0 now, which it is. So yes, our center realigns. So now it just becomes a problem of plugging in x squared plus 3 to the equation. So g of x is going to be approximately this new polynomial, and we already named this polynomial up here p, so we'll call this one t. And we know this is equal to f of x squared plus 3, and we're just going to plug x squared plus 3 into each of the x's. So we have negative 4, 2 times x squared plus 3 minus 3. Well, the plus 3 minus 3 will cancel, so it just becomes x squared. And that's going to happen to every single one of these. Oops, squared. That should have been to the third earlier. Oh my gosh. Cubed over 6. Now, technically, this is not a good notation anymore. We're saying t3 of x, but this is not the third degree polynomial. Luckily, we're able to name our functions whatever we want as long as we name it, realign it with what it told us earlier. So it told us g. We're saying this is an approximation for g. So this should be fine. But technically, our n has now changed to 6. So this would be the 6th degree polynomial, would be a better way to say it. Okay, last one we're going to look at. Once again, I'm going to pause and go ahead. Oh, no. We're going to talk about A because A is interesting. A is asking what each one of these values are. Now, the reason I say this is interesting is a lot of people will just look and start immediately grabbing these values in front. But we need to remember what each of these equal. So 2 is just f of our center, which is 4. So that's fine. F of 4 is 2. But f prime of 4 comes from the x term. So it should be f prime of 4, x minus 4 to the 1 over 1 factorial. Well, we don't see that term anywhere in this problem. So we can make a conclusion about f prime of 4. Well, what happened to f prime of 4? F prime of 4 had to have been 0. All right, similar thing we can do for each of them. F double prime of 4 should be with the x minus 4 squared term over 2 factorial. Well, here's the x minus 4 squared term, so that must mean it's negative 5, right? Well, that's not exactly correct either because it's f double prime of 4 over 2 is equal to negative 5. Well, now we can do a little bit of algebra and say, oh, this is supposed to be 10. So f double prime of 4 is negative 10. Then the same thing with the third derivative. We know that the 8 here at the end should be f triple prime, the third derivative of 4 over 3 factorial, because the x minus 4 cubed is just its own thing. So that means this should be 24 is equal to the third derivative at 4. Okay, and now for B, we have, does f have a local minimum, local maximum, or neither at x equals 4? So now we have to go back and think about what does it mean for a function to have a local min, local max, or neither. Well, first, the derivative has to equal 0. Here's the derivative equals 0. F prime of 4 equals 0. So we got that. 0 or undefined, but undefined wouldn't work in this case. 0 is what we need. Then we need to think about what it's doing. It should change from increasing to decreasing or decreasing to increasing. Well, the issue is we don't have enough information to figure that out. Instead, we have another test that we used around the same time of when we learned that also found relative extrema. It was the second fundamental theorem of calculus, which said if C is a critical number, which it means the derivative is 0 undefined, then if the second derivative of C is positive, it's a relative min. C is a relative min. And if the second derivative at C is negative, C is a relative max. And if it's 0, well, then that doesn't tell us anything. But this is hopefully what we want to get. Well, luckily, we have information about the second derivative right here. The second derivative is negative 10, which is less than 0, which means x equals 4 is a relative max. Okay, so all different examples of some information you can gain from these Taylor polynomials. Please let me know if you have any questions when you get back into class. Y'all have a great day.